Hello and welcome to the planetary spectrum generator video tutorials. I'm Thomas Fauché, member of the PSG team and expert of atmospheric modeling and exoplanet science. The subject of this video is a treatment of the atmospheres, exospheres and comets within PSG. For more information, you can refer to the third chapter of the PSG handbook. PSG handles two distinct types of atmosphere: hydrostatic equilibrated atmosphere, which are typical for planets and exospheres, or expanding comas that are typical of comets and small bodies. The user can provide any atmospheric composition structure, yet the users can also choose from a wide variety of templates and integrated climatology models. The vertical profile of the atmosphere is provided by the atmosphere layer keyword, and the connection between this profile to the species listed in the atmosphere gas field is done via the scalar abundance unit in the atmosphere unit keyword. It is important to note that only molecules included in the atmosphere gas and atmosphere aeros keywords will be included in the simulation, independent of the species included in the vertical profiles. For hydrostatic equilibrium atmospheres, if the variable altitude is not provided for the vertical profile in the atmosphere layers molecules keyword, then PSG will compute the layer altitude by employing the hydrostatic equation. A constant molecular weight for the whole column is defined by the atmosphere weight keyword. Yet the user can operate with varying molecular mass atmosphere by providing the altitude value for each layer. The surface pressure indicates where the atmosphere starts, independently of the provided profile pressures, while the provided planetary diameter and gravity also refer to this pressure surface point. Details on how to build a config file in PSG via those keywords are discussed and explained in chapter 1 and the first video of this tutorial. PSG can simulate the relative transfer in any kind of atmosphere. So let's go over the main general types. The first one, for Earth, PSG computes telluric transmittances and radiances by extracting atmospheric profiles and molecular abundances from the MERA2 database, which is constantly being updated, but with a latency of approximately 2 months. Therefore, for atmospheric requests before 1980 or newer than present minus 2 months, PSG will extract information for the same season, location, time of the day, but for the nearest year available in the database. PSG considers a large amount of species that you can see on the screen right now. PSG also integrates Mars atmospheric data using the Mars Climate Database, the MCD, and the GEM General Circulation Model, and they are both comprehensive repositories of meteorological fields derived from the GCM simulation and combined with observational data. Specifically, PSG extracts vertical profiles of pressure, temperature, molecular abundance, dust size, water ice, and ice particle size from the GCM databases, while the surface albedo information is determined from several orbiter databases. For gas giant planets and dense hazy atmospheres, the main opacity terms that define their optically thick surface are hazies and the effect of collision-induced absorption by molecular hydrogen and helium. Beyond that, a plethora of hydrocarbon species and other trace molecules contribute to the overall atmospheric opacities. Due to this set of numerous opacity terms, these atmospheres are rarely probed at pressure beyond 10 bars. And in PSG, we have provided a basic description of the main hazies and species from 10 bars to about 10 nanobars. For cometary atmospheres, PSG includes many processes, such as an expanding exosphere structure, photodissociation processes for parent and daughter species, extended icy grain structure, thermal, equilibrated, and rotational emission, and also emission computed from non-LT cascade fluorescence models. These processes are integrated by incorporating realistic outgassing models and cometary excitation radiative processes. More detail in chapter 3 and 4 of the handbook. PSG can also compute the relative transfer within exoplanet atmospheres. PSG organizes the exoplanet by mass and density into 4 categories: Earth-like, super-Earth, Neptune, and gas giants. Currently, PSG simply assumes a terrestrial structure and composition for Earth-like planets, and a Venusian structure and composition for the super-Earth-like. For gas giant, PSG employs a non-gray thermal model. So once the temperature profile of the exoplanet is defined, PSG employs the chemical equilibrium equation of state for a wide range of metallicities and primordial states. This implementation provides an a priori vertical profiles for dozens of species. It is important to mention that PSG includes the Global Emission Spectra, the GLOBS module. It helps to ingest 3D atmospheric fields simulated by GCM. To use GLOBS, a set of 5 steps have to be followed. First, you have to run a GCM model in your personal machine or cluster and store the resulting 3D field and parameters into a GCM formatted file, which is typically a netcdf file. Then, by employing a script available on your GitHub, you can convert GCM netcdf file into PSG GCM binary file. Several example conversion scripts are available at the GLOBS application site, permitting to convert netcdf output files from Rocky 3D, LMD, and Exocam GCM from your local machine. Then, in the GLOBS site, you can upload the PSG GCM file by clicking on Load GCM Data. If the upload process was successful, the site should display graphically the GCM outputs for different variables. Then you can select the observing geometry, which could be transit or direct imaging, or you can even do it on the target and geometry section of PSG. You can also verify and update the molecules and aerosols to include in the simulation by visiting the atmosphere and surface section of PSG. In the GLOBS site, click now on Generate 3D Spectra. For each position on the planet, the algorithm will update the atmospheric profiles, surface properties, and geometry parameters and will run the radiative transfer. These results will be integrated employing the appropriate weights. Results will be displayed in the home site of PSG. Finally, it is important to adequately set up the binning parameter. It allows to speed up the calculation by horizontally binning the GCM data to have less PSG radiative transfer calculation. Higher binning means more aggregation and less PSG radiative transfer calculation. High binning, which is number above 50, should be only used when testing. A binning factor of 3 is typically recommended, leading to a binning of 3 pixels by 3 pixels and a speed up of 9 times while sacrificing a little accuracy. However, you will be limited to 200 pixels for the radiative transfer calculation and to a size limit of 50 MB for your GLOBS binary file. You can also run the GLOBS module in script mode via the API. You will find the necessary scripts in GitHub. Hopefully you found this short video instructive. We encourage you to explore the handbook chapter 3 in detail and also to check other learning video and online material. Thank you.